These are our pre-calculus notes, 05, Systems of Linear Equations and Inequalities. So this should be a review section. This is really a review, honestly, of Algebra 1 at this point. But I know sometimes it's nice to have something to look back on, and you will find that some of the solving is a little bit more difficult. So with this first one, we want to solve by graphing. And my equation is in standard form. I have x and then y and then a number across the equal sign. And so normally, like I would make my y equal to 0 and I'd find my x-intercept. But I could tell that my x-intercept is going to be a fraction. So if I was just trying to sketch a quick graph, that'd be okay. But because I'm trying to solve this way, and by solve we mean find that xy ordered pair, I need to actually have a better method for graphing. So I'm going to go ahead and just solve it for y and see what we come up with there. So if I want to solve it for y, I'd subtract my 4x. And then, this is a positive 18 to start with. So negative 4x plus 18. And then because I have a negative y, I'd go through and change my sign. And it's very graphable now. I have a y-intercept, I have a slope, except my y-intercept is negative 18. It's not going to fit on this graph. So what I'm going to do instead is I am just going to pick an x value, and then I'm going to solve for the y. So I'm going to basically just find an ordered pair. So I don't want to do, I would pick nothing that's negative. We want it to be easy. And I have to think about how this graph is crossing at negative 18 and then going up. So if I pick something that's bigger, like 3 or 4 or 5, I'm going to actually be able to graph it. If I pick a small number like 1, 4 times 1 minus 18 is still going to give me a negative number that doesn't fit on my graph. So I'm just going to pick like x equals 3. So if x is 3, then y is going to be 4 times 3 minus 18. 12 minus 18, that would be a negative 6. And so I have 3, negative 6 is going to be a point on my graph. So I'm going to go ahead and graph that really quick. 3, 1, 2, 3, 4, 5, 6. And then I could find another point, or I could just use my slope. So at this point, I know my slope is 4 over 1. So from this point, I am going to do a slope of 4. And so now that line's graphed. And then for my other line, I have the same issue where when I go to find my x-intercept by making my y equal to 0, 3x equals 20 would give me a decimal, which I don't want. When we're trying to solve by graphing, we need it to be a pretty exact graph in order to tell what's going on. So I'm solving for y. So let's see, we have y equals 3/4 x. I can do 20 divided by 4, so this one's going to be okay. So I've got y-intercept of negative 5 and a slope of 3/4. And then right away our graphs cross. So this is going to be my solution. It looks like 4, negative 2. And I want to write that as an ordered pair. And if I go back and check, it's going to work in both equations. So don't forget that you're allowed to do that. Even as we come up with more sophisticated or complicated ways to solve this chapter, you can always go back and it needs to work in both equations to be a solution. So second one is solve by substitution. So I'm going to get an x or a y by itself. We could solve for this negative y, we could solve for that way, we could solve for this one. I feel like the one in the second equation is easiest to solve for. So I'm going to let that be y equals negative 2x plus 22 by subtracting 2x on both sides. And then I'm going to substitute this into the other equation, into the first one for the y. So we have 3x minus a negative 2x plus 22. Notice I had to put that in parentheses because I'm subtracting all of y. And then I'm going to have to distribute that minus sign. And then we'll go ahead and add 22 on both sides. This was a 2x here, so this is a 5. 5x equals 30. Divide by 5, x is 6. Once I go back and find my x, I need to find my y. So y equals negative 2 times 6 plus 22. Negative 12 plus 22, y equals 10. And I could, again, go back and I could check my answer. And if I check, it has to work in both systems, my whole system, both of my original equations. So next is elimination. Elimination is when we figure out how to add or subtract these equations together, and we never let you do subtraction. We always make you do addition. So one will have to be negative, one will have to be positive to eliminate a variable. So if I wanted to eliminate, say, my y's, then I would multiply the top equation by a positive 2. So then I have 10x plus 4y equals, let's see, 680. I'm going to rewrite my second one. I'm always keeping my first equation first, my second equation second. We're really trying to do a good job of keeping track of these and setting up good work habits for systems of 3 equations. So when I add together, my y is eliminated because negative 4y plus 4y makes a 0. So 13x equals, let's see, 1040. Divide by 13 and x is 80. And then I need to go back and find my y. I can use any of the equations. So the only equation I definitely wouldn't use is this one here because I've multiplied it by 2. That's going to give me bigger numbers. It's going to be harder to work with. So I want to pick one of the 2 for my original system. And you can use whatever one looks easier. So it has to work in both. If you use either equation, you'll get the same answer. But I want to pick the one that looks easiest. So I'm going to pick the first one because it's all positive. And then I'm going to take my solution for x and substitute that in. And this should all be review. I know that the last couple of years in math with COVID have been strange, but this should all be review. And we're not showing the adding and subtracting anymore in Precalc, but we're still not skipping to just the answer or anything. So we get 80 comma negative 30 here. This next one is a system of 3 equations. So with a system of 3 equations, what we do is we work with 2 of them and we cancel a letter out. And so when I look at these, it seems like my x's would be really easy to cancel. So I'm going to take my equation 1 and I'm going to add equation 2 and see what I get here. So let's see, x plus y plus, I need to move this up a little bit, z equals 5. So I am canceling out my x's, and I could pick any variable to cancel it. I don't have to cancel out x. I just need to be consistent. And so my x's are gone. I have 2y minus z equals 0. So I have not yet used equation 3. So I have to use equation 3. I can match it with either 1 or 2. And I need to also cancel my x's out. So I'm thinking because this one is already negative, it's going to be easiest to do 3 times that one. So I'm going to do 3 times equation 2 plus equation 3. And that's going to give me another equation without x. So I'm going to take equation 2, multiply it by 3. And then I'm going to write down equation 3 underneath it. So notice I'm putting 2 and then 3. I'm kind of writing some directions here about what I'm doing so that somebody else could follow my work. And when we add, we get a positive y minus 5z equals a negative 18. So now I have 2 equations with only y and z. That's going to be my new system. So I'm going to use these equations with only y and z, and now I'm going to put the 2 of them together and solve again. So I think it's going to be easiest to cancel out y, which means I need to multiply the second one by a negative 2. So then I rewrite the whole system again. So there's more writing this way. I know it's tempting to just skip that part, but that's how we make mistakes. So when we add together, now my y's eliminate, and I have a 9z equals 36, which means that z equals 4. So then once I find z, I want to go back to this system and find y. So I'm going to use 2y minus z equals 0. And I'm going to solve that. So I put the 4 in for z. And then once I find y, now I go back to the very first system. And so I think the easiest equation to work with is the first one, but you can use any of them. Like math should just work. It doesn't matter which equation I pick. So if my x plus y plus my z equals 5, then I have x plus 2 plus 4 equals 5. And that means my x is negative 1. And so I have a triple now. So instead of an ordered pair, I have an ordered triple, which is an x, y, z, all in parentheses. So negative 1, comma 2, comma 4. So next is a little bit of vocab. And we used different words in Algebra 1. We just talked about many solutions, no solution, that kind of stuff, but there's actual vocab for that. So consistent with the system of equations means there is a solution. That means inconsistent means that there's no solution. So if a solution is consistent, there's two different types that we can have. Independent is when there's exactly one solution. And dependent means there's many solutions. Now, I guess if you look at systems of conics, I mean, it would be possible to have exactly 2 or exactly 4. But we have vocab for these two different scenarios, for exactly 1 or many. So now we're just going to go through and take a look at a couple different examples of this and just see what's going on. So I want to go ahead and try solving, and then this is giving me a clue that I'm going to get weird answers. So I'm just going to approach this like I normally would. If I wanted to cancel out, say, my x's here, if I want to eliminate them, I'd multiply by -3. And then I'm going to rewrite my second equation. I'm always keeping them in order. And when I add, I get 0 equals 0. Well, that's true. So it means I have many solutions. I really have the same line. That's why they completely canceled out, because it's actually the same line. So I have many solutions. When they graph, the lines are right on top of each other. That's why there's many. Every point on the line, every xy ordered pair that works in the equation for the line is a solution. And then using my new vocab, that means it's consistent because there is a solution. But because each solution is dependent on all the others, it's dependent. So that's when there's many. Okay, on the next one, I'm going to choose to eliminate x again. And I'm going to get a tiny different result this time, because now when I add, I don't get 0 equals 0. I get 0 equals 3. And we know that that is not true. So that means there's no solution. These must be parallel lines if I'm thinking about the picture of what's going on. And so it is inconsistent. So for the last two, we're looking at solving systems of inequalities, where we do that by graphing. And then our solution is going to be where the lines cross, or where the graphs, the shading crosses, where it's overlapping. So if I have a less than or equal to or greater than or equal to, remember those are solid lines. If it's just greater than or less than without the line underneath, that's when it's dashed. So first I just want to go ahead and graph my lines. So greater than or equal to 2x plus 1. So y-intercept and slope, and I can just connect it with a nice solid line. And there's a couple different ways to look at the shading. One way is to plug in the point 0, 0 and see if it's true or not. So if I use 0, 0 for the y is greater than or equal to 2x plus 1, I would get 0 greater than or equal to 2 times 0 plus 1. So 0 is greater than or equal to 1. So that is not true. So I would not shade on the side of 0, 0. I would shade on the other side, which is going to be above. And you could wait and do your shading at the end. You don't have to do the shading as you graph. You could just shade only the overlap. The other way is I could think about how this says y is greater than or equal to. And so if the 2x plus 1 is that line, y greater than that means it's going to be up from that line. So the second one is less than or equal to 1x minus 5. So 1, 2, 3, 4, 5, and a slope of 1. And I'm not making a real neat line here. I can tell I'm going to have to extend this a little bit, I think, to get some overlap. And so for my second one, it says y is less than or equal to. So I know that I'm going to be shading down. And the other way I could figure that out again is using a point not on the line, like say 0, 0. We like to use 0, 0 because it's easy, but it has to be a point not on the line. So if this was a point on the line, I'd have to pick a different point. So if I put in 0, 0 less than or equal to -5, well, 0 is actually greater than -5. So again, I don't shade on the side of 0, 0 when I'm looking at this line. I need to shade on the opposite side, which would be down here. And so my overlap is actually this region right here where I've got the double shading, and that's going to be my solution. Last problem. The first one looks really similar, greater than or equal to 2x plus 3. And this is equal to again, so solid line. So much easier when the lines are solid. And it says greater than or equal to, so from this line, I'm going to be shading up. Greater than for y is up, less than for y is down. I'm not even bothering with colored pencils. Less than 2x minus 1. So that's going to be a dashed line. And less than that would be down. Now, I've got kind of an interesting issue here. They both have a slope of 2. I've got different y-intercepts, so my lines are parallel. And because of the shading, I am shading like above one and below the other. So there's actually no overlap. So this is going to be no solution. So this is the end of our 0-5 notes. I hope that you remember what you're doing. Please ask for help in class if you need it.